So here's an answer to the homework questions on damping and resonance. So I'm going to go through each of these questions and go through the answers. So question 1AI, we've got A equals minus 2 pi f squared x. Now, probably the most important equation in simple harmonic motion is A equals minus omega squared x. Whenever anything is a simple harmonic motion, this relationship will be true. So I'm hoping you can see from your circular motion that you kind of, as soon as you see 2 pi f, you're thinking, oh, that's going to be omega there. So we can see that equation right there. A is the acceleration of the object. F is the frequency with which it oscillates, or the number of oscillations completed per unit time. And x is the displacement from the equilibrium point. It's not distance because it's a vector, it's positive and minus, and it's not amplitude either. The amplitude is the maximum displacement, just as we have with waves. So the minus sign is important in simple harmonic motion, and that tells us that the acceleration and the displacement are in opposite directions. This is really, really important, and if this wasn't true, it wouldn't be an oscillator. If we imagine a pendulum swinging backwards and forwards, what we do is we have a displacement x in that direction. It's been displaced to the right. Now the acceleration has to go in the opposite direction. If it didn't go in the opposite direction, it would just fly off and it wouldn't oscillate. Something that oscillates always got to move back to its equilibrium point and then beyond. So that's the significance of the x and the minus points there. Or you can say that A is always directed towards equilibrium point. That's the same reason, really, because x by definition is in the opposite direction from the equilibrium point, how vector quantity of how far it is from the equilibrium point there. Question I, calculate the maximum speed of an electron which is oscillating with simple harmonic motion. So we've got a frequency. So frequencies don't often come up in SHM. We're quite often dealing with angular velocities there, and we've got an amplitude as well. So the equation V equals minus A omega sine omega t is where this comes from. And what we want to know is we want to know the maximum speed. So we want to know when this function is at a maximum. Whilst A is a constant, the amplitude, we're assuming it's damped here. It doesn't say that in the question, but you need to assume that. Omega, the angular velocity, is a constant as well. It's the sign that changes over time. The maximum sign is 1, so that just drops out of our equation. And what we can write is we can write Vmax equals minus A omega. I think this is actually on the formula sheet, but that's the origin of that equation there. So the amplitude we've got in this question is 8.0 times micrometers, which is 10 to the minus 6, multiplied by omega, which is equal to 2 pi f, which should give us the answer 2.5 times 10 to the minus 3 meters per second. So that's the maximum velocity of this object there. That's question number 1, I think. Oh, B. So this is a weighted test tube. This does come up occasionally on the A-level course. So imagine you've got a beaker of water. The weighted test tube is, you've got the test tube there, and in the bottom you put lead shot or something very, very dense that keeps the test tube up and down. So what you would do is you would just push down slightly on that test tube, and then what that test tube would do would be bob up and down in the water there. So we've got an equation here for the frequency. First of all, we need to show that this is homogeneous with respect to units. So really, the first place to start with this, with any equation, is square roots are not particularly nice. So what I'm going to do to start with is I'm going to square everything. So I've got 4 pi squared f squared equals a rho g over m. Now, when we want to put this in units, we've got to be careful not to use an equal sign because they're not equal. Frequency is seconds to the -1. I could put hertz in there, but we need to cancel stuff either side. So we're going to go seconds to the -1. Now, the cross-sectional area, A, is going to be in meters squared. Rho is the density of water, which is mass divided by volume, kilograms, meters cubed, G. Now, we could either have newtons per kilogram, or we can have meters per second squared. Now, we have got a kilogram there. I'm thinking we're going to have a kilogram on the bottom from the mass. So I'm thinking, because we've got lots of meters and we've got seconds on this side, I'm going to go G in meters per second squared. Units of acceleration divided by kilogram on the bottom. Now, having things on the top and bottom is not particularly nice. It's easier just to cancel that, and we've got everything on one row. And then what we want to do is we want to expand these things out. So we have seconds to -2 equals, now we've got meters to the +2, meters to the -3, meters to the 1. So we'll add the powers here. So 2 minus 3, -3 is -1, add 1 is 0. So the meters all cancel as well. Okay. There, and what we've got now is all we're left with is the seconds to the -1. Okay, and what we've shown there is we've shown that this is homogeneous with respect to units. The units on both sides are the same. Therefore, this equation could be true. If it is not homogeneous, the equation is definitely incorrect. It shows it could be true. It doesn't mean it is true. It just means it could be true. Because, for instance, you notice we just drop out this constant here. So, I mean, that could be, someone could write an equation where that was 8 pi f, and that would be wrong, but it would still be homogeneous because we ignore the units. We ignore the constants in our homogeneity here. So, the next question, if you haven't watched my video on exponential decays, I suggest you do now. Okay, and when you've watched it, come back and have a go at this. But what we want to do is we want to show that this is exponential, and we want to show that it decreases by an equal fraction in equal periods of time. So we can see straight away that the time period is constant for this one. The person writing this question has given us a nice graph. So what I'm going to do is I'm going to construct a table, and I'm not even going to use time, I'm just going to use number of oscillations, because there they are the same. So I'm going to go, just move that up a bit so you can see, 0, 1, 2, 3, 4, 1, 2, 3, 4, and then I need to write what amplitude is at that particular point. So that is 5.6. This one here is looking like 3.6. This one here is looking like 2.4. This one here is looking like 1.8. And then this one here is 1.2, I think. So what I'm going to write here is I'm going to work out what the fraction remaining is for each one. So for this one, I'm going to go 3.6 divided by 5.6. I'm going to write a n divided by a n minus 1. So the amplitude divided by the previous amplitude. So 3.6 divided by 5.6, 0.64. And then for this one, I'm going to go 2.4 divided by 3.6. Gives me 0.67. And then for this one, I'm going to go the amplitude divided by the previous amplitude. 1.8 divided by 2.4 divided by 2.4 is 0.75, and then this one 1.2 divided by 1.8 0.67. I'm assuming I've read my numbers off the table correct here. So we now need to come to a decision about whether this is exponential or not. Is there an overriding pattern? Are they getting bigger or smaller? No. This one seems a little bit of an anomaly, but since I wasn't reading the graph that accurately, I think we could say it is exponential because we would write it is exponential as after equal periods of time it has lost an equal fraction of, I can't even read what I'm writing here, of its amplitude. So the other way of doing this, I wouldn't really recommend this, it's not as clear to show, is to sort of go through an equal fraction. So how long does it take to go to 3/4, like you would with half-life would be the other way. That's perfectly acceptable, but I don't think you get the good results as with that. Question part 3, don't worry about that, we haven't done energy yet. We'll be doing that next lesson.